This is Pete Ryan. I'm Kira's advisor. And I'm going to start by introducing Kira and a little background on the project. And then Kira will give about a 20-minute presentation. And then there'll be time for Q&A from the assembled masses here, friends, family, and others, colleagues. And then after that, we'll ask that everybody leave and do a formal thesis defense like we do in Geology department. So first, welcome everybody, 36 people. That's really nice to see so many faces and names, familiar faces and names. I want to provide a little background on this project. And the background is I've been working in Costa Rica for almost 20 years, and much of that time enabled by a good colleague named Guillermo Alvarado, who is more of a volcanologist than somebody who studies soils along the tropical coastlines, but I dragged him into that. And now he's dragged me into some things closer to volcanoes. And one of them is the occurrence, as Kira will talk about, of aquifers with high amounts of seemingly naturally occurring arsenic. And given that we have the capacity to test for arsenic here in the labs at Middlebury College, or 4 miles down the road at Middlebury College, Guillermo and I started talking about possible ways to address the origins, trying to understand where the arsenic is coming from, which is part of the solution, I suppose, is first to understand the origins of the problem. And somewhere around the same time, I was actually in Costa Rica this past summer working with Guillermo on some projects, and Kira got her own funding. She worked to get funding through the URO, Undergraduate Research Office, got her own funding, flew down to Costa Rica, met me and my wife Maggie down there, and we carried out about 5 days of field work from kind of hot lowland environments to slightly cooler upland environments, sampling volcanic pumice flows, tuffs, paleosols, all kinds of really interesting rocks, and mailed back to Middlebury College many samples that Kira and I eventually parsed down into a set that seemed like it would answer the question. And she spent a lot of time in the lab over the past 6 or 7 or 8 months, really poured it on in the end with her foot in a cast, and managed to come up with a really nice data set that I'm going to say, I have not shared the results with Guillermo yet, but I think it's some really exciting stuff that she has found that I don't want to steal her thunder anymore, but to say that it's been a real pleasure working with Kira this year. We have some shared interest in arsenic. She had a great internship last summer working on arsenic. I've been working on arsenic for a long time, so there's sort of an academic connection, but there are connections that go beyond academic, connections that have become like family, connections that have been centered around basketball, and sort of some shared values of how to do life. And it's been a great pleasure for me. It's really enjoyed this experience, and I don't want to take any thunder away or give any results away, so I'm going to turn myself off now and hand you over to Kira, who will give a 20-minute or so presentation and then be willing to take all kinds of questions from any that you may have. So Kira, take it away.
Awesome. Thank you, Pete. That was really sweet. I really appreciate it. I'm going to share my screen with you all, so hopefully this works out. Alex, you're the one I see. Can you give me a thumbs up if you can see my screen?
That looks good.
Sweet. Okay, let's pin myself. Hello and welcome, everybody. First off, thank you so much for being here. I know I would not have been able to accomplish any of the last year or this thesis project without any of the 39 of you. So I'm so fortunate to have you all in my life, and just really grateful for this opportunity to share something that I'm really passionate about. As Pete said, we share this interest in all sorts of things, but this is definitely among the most interesting things that I've ever worked on, and I'm excited to share with you all. So first off, I will just reiterate, my name is Kira, and I am gonna present my thesis research through the Middlebury College Geology department, which I've been working on for the last year. And the title of my research is Analysis of Volcaniclastic Sediments as a Potential Source of Groundwater Arsenic in the Guanacaste region of Costa Rica. And I want to give a shout out, of course, to Dr. Pete Ryan, who was the main collaborator on this project, as well as Guillermo Alvarado down in Costa Rica, who helped us with all sorts of things, and we're really excited to share the data with him. So I want to start out by telling a little bit of a story, and that story is the story I call it a story of two towns, you could say. And in 2010, a geochemist named Herrera Murillo did research trying to show what was in the groundwater supply in Costa Rica. And he found that in the Guanacaste province, which I'll show you in a moment, in the northwest corner, which you can actually see on this globe back here, that there were high levels of arsenic. And what high levels of arsenic means is anything above the World Health Standards 10 parts per billion. So in Costa Rica, 88% of the population rely on drinking water, crop irrigation, food preparation, and agricultural purposes on the water that comes from their groundwater wells. So that's a lot of people. And especially when it has levels of contaminants that exceed this 10 parts per billion, it obviously invites a certain amount of attention and concern to the area. So that's the first, that is the first thing that happened. So after 2010, once the data was released that said there were places in Costa Rica that had these high levels of arsenic, there started to be a little bit of a media frenzy. So over the last 10 years, there has been lots of reporting and media focused on the lack of research, the lack of knowledge, and the lack of medical attention to this province in Costa Rica, in which arsenic was causing a whole sort of issues, but especially the health effects that were most notable. In the short term, when someone is contaminated by arsenic in their blood supply, it can result in skin lesions and other skin defects, which you can see in this, well, it's under there, in that photo right there. And then in the long term, it can have effects such as being potentially carcinogenic, causing diabetes, and have other impacts on cognitive development, both to children in utero, along with just people. And so once this media frenzy has kind of developed over the last 10 years, as you can see, this one was published in 2019, so still going on, they were able to pinpoint the two towns that had the most arsenic contamination in their wells. And like I said, this is the story of two towns. So Bagaces and Cañas, as you can see on the map right here. In the town of Bagaces, 56%, which is like over a dozen wells, tested. So these are local groundwater wells, public, community, and private, tested to breach the level of arsenic contamination of 10 parts per billion. And in Cañas, it was over 50% of the wells tested positive for leaching, for having higher levels of arsenic contamination. Bagaces is the fourth largest canton or pueblo in Costa Rica, in the Guanacaste province, and it's home to 17,000 residents. And Cañas is the sixth largest, and it's well populated and home to 30,000 residents. So obviously, because 88% of the population rely on this water, it made the people really upset. So in 2013, there was a strike in which the People's Voice of Bagaces organized a time for people to take to the streets and really demand answers. One of the presidents of the organization was quoted asking for someone to tell us what is killing us, what is in our water, and what is in our environment. And so that is what sparked, obviously, Pete and Guillermo's interest in this region and in this project, and of course is the guiding research and really guiding purpose for me in conducting this last year of research. So that leads me to my guiding question. What is the source of the arsenic in the groundwater supply in Bagaces and Cañas, and what is the fate and transport of the arsenic? In order to do this, I conducted an integrated geochemical approach, which we'll delve into more in a moment, to understand the volcaniclastic sediments of the area, unearthing what the trace elements, major elements, and rare elements are of the sediments in that area, trying to see what the source of groundwater arsenic contamination is. So just to situate us a little bit further, as you can see, Costa Rica lives right on the convergence of the Cocos Plate subducting underneath the Caribbean Plate. And this subduction region has caused the formation of the Central American volcanic arc. As you can see, this line of volcanoes that runs northwest, southeast throughout Costa Rica. And the Miravalles volcano specifically, which is where most of the research was conducted, is an andesitic stratovolcano that reaches about 2,000 meters and has been relatively dormant over the years, but in 2016 there was a reported lahar And the research I conducted was in the lower distal flanks of the Miravalles volcano, so pretty much southeast, southwest of the volcano. Cañas is right here, and Bagasse is right here. So moving right along. So in order to kind of focus my research, I did a extensive analytical review of literature in order to understand what the potential source of arsenic could be, and that led me to the answer of volcanic glass. So over the last 20 years, there has been lots of research done specifically in Argentina, but also in other places in the Andean forelands that linked volcanic glass as this potential source of arsenic. And I used data from the environmental geochemistry class in 2018 in order to prove that in my own understanding. So I'm going to take a second now to explain this graph to you all. This is a laser ablation ICP-MS scan, which pretty much shows, so the x-axis here is the count time as the laser beam goes across the polished piece of pumice. Right here we have an SEM image of the polished piece of pumice, and the y-axis is the intensity of a given element. So how this works, let's say my mouse is the laser. As it goes across this piece of pumice, it detects what elements are in it. And for the scope of this project, we decided to compare volcanic glass to plagioclase and show the different chemical compositions of these two mineralogical phases. So what you see right here, this kind of wispy, hairy looking stuff, is volcanic glass. And I'll explain in a moment why it looks like that. But so as the laser went across this, first it detected the gray here shows the background. So we have low levels of pretty much everything. That's just like a blank sample. And then it hit this big piece of plagioclase, and we saw spikes in strontium, sodium, and calcium. And as it continued to go across the piece of polished pumice, it went back into this glassy area in which we saw spikes in lanthanum, barium, potassium, and of course, arsenic. And so this is part of the reason we are able to focus my research into volcanic glass as the primary solid phase of arsenic. I will note quickly that for some of you that might know this, obviously these elemental intensities are a bit skewed just to show relative abundance, but in a piece of plagioclase, you're going to definitely have more sodium than strontium, but this is just a graphical representation. So using the prior research and the data produced by the environmental geochemistry class, I was able to guide my investigation into volcanic glass as this primary source of arsenic. So some of you might be wondering what volcanic glass is. Great question. So volcanic glass is the amorphous, uncrystallized product of rapidly cooling magma. So it's as the magma cools, it's like the first thing to quench. So the magma erupts from the volcano and it grows crystals as it is cooling, but volcanic glass is before any crystals are grown or packed together or even ordered in certain crystal lattices and arrangements. And the volcanic glass is kind of this just silicate dominant liquid that has quenched. And so this is what we are calling our first source of arsenic. Methods. So as Pete mentioned, I was able to go down to Costa Rica for a week last summer with Pete and Maggie to conduct research thanks to the Waldman Fund through Middlebury College. And during my time there, we spent all of our time in, like I said, the lower distal flank of the Miravalles volcano, collecting 79 total sediment samples from 16 different locations, 9 upgradient of Bagasse, and 7 upgradient of Cañas. And these locations were selected with the help of Guillermo Alvarado. We wanted to pick sites in which the volcaniclastic sediment of the region was analogous to what was in the actual regional aquifer. So all this stuff is up gradient of where the wells actually are sourcing the water from, so that we can see how the water percolated through these sediments down gradient to get to the wells. And thanks to Guillermo a lot for helping pick the sites. So these are a couple field diagrams of what we were able to do. These are 2 sites that represent the whole host of samples we were able to collect. We collected a diversity of samples trying to aim for some stratigraphic differences, but ended up mostly with pumice flow and ignimbrites, as you can see in 10A and 10B, and the top section of the samples collected at 14. In addition, we were able to collect a lot of paleosol, which is this more red-orange kind of burnt-looking stuff in this region, which paleosol is the soil of the past that has been deposited and pressurized to kind of create the rock of the area. So this is the altered over time soil that turned into part of the regional aquifer. So moving along, I conducted a lot of lab work over the last year. I used X-ray diffraction in order to parse out negligible glass content and significant glass content in order to get a host of samples to go on to the next round of mineralogical and chemical analysis to understand what the glass was leaching and what was contributing to it. So I wanted a range. I then used the NeoFluxer, which helped prepare my samples for X-ray fluorescence and inductively coupled plasma mass spectrometry. And I used all these analytical tools to further understand what was making up these sediments and the chemical signatures of them, including trace elements, major elements, and rare earth elements, in order to, of course, get to what the source of the arsenic is. So what did I find out? First, I want to walk us through this X-ray diffraction pattern, which is showing a breadth of the samples of varying glass content. So like I said, I used the XRD to choose a host of samples that had different amounts of glass to see if the glass was actually what was causing the arsenic. And to explain this for a moment, on the x-axis, we have the angle of diffraction, which is basically the crystallographic spacing between different kinds of minerals in the sample. And the Y intensity, similar to the laser ablation, is the intensity of the peak. So the intensity means that there's more of it. As you saw earlier, volcanic glass is this amorphous mineralogical phase that doesn't really have specific crystals in it. And so based off of methodology produced by Andrews et al., this volcanic glass area in the purple, you can see between 15 and 32 theta, is kind of just this amorphous hump that shows that there's this mix of minerals and this mix of elements that turn into the volcanic glass hump dominated by this silica content. In comparison, we use zincite as our standard. So all these zincite peaks should calculate to 10% of the overall sediment based off of calculations, and therefore we were able to discover how much volcanic glass was in each sediment. I also quickly want to point our attention to smegtite and kaolinite. Smegtite is the first weathering product of volcanic glass, so as it begins to change and get chemically altered, we first see a hump of smegtite, and then as smegtite continues to get altered, we then see the presence of kaolinite. So looking at this graph, we can see as we go down in volcanic glass content, we see the big, broad glass hump here to almost negligible glass hump here. We see an increase in weathering as the volcanic glass changes into smegtite and then eventually into kaolinite. So this allowed me, like I said, to pick a suite of samples in differing glass content to move on to the further chemical analysis. So like I said, I chose 19 samples for further analysis. This is a graphical representation of the samples showing the wide range and the overall trend of high glass content to low glass content. I will just mark for anyone that notices these glass contents are quite high, and that's because it was difficult to totally get just the glass hump and erase kind of all this background or other potential minerals that are not important to the scope of this thesis. And so overall, we had a nice range of glass content. Here is a couple field samples which had the highest glass content. As you can't totally see the glass specifically, but these are just pumice-rich samples with high glass content. So this then led me to the work with the ICP-EMS and the XRF, in which I was able to test the chemical signatures and specifically the major element compositions. So I used SiO2, which is a very mobile in tropical soils, to compare to understand what is allowing the glass to break down. And there were two main things I noticed. So the first thing I noticed was the inverse correlation of SiO2 with iron, titanium, and aluminum. So as you can see, these three graphs, as weathering increases, so does iron, titanium, and aluminum, which also means the decrease in glass content as shown by SiO2. The second thing I uncovered was the positive correlation of SiO2 with potassium, sodium, and calcium. And we'll get into this more in a moment, but overall, the reason for this is because these three elements are relatively insoluble. So as the glass, which is really soluble, is weathering away, these insoluble elements are staying whole. And on the other end, these three elements, potassium, sodium, and calcium, are relatively soluble. So as the glass is eroding away, these elements are leaching out into the water. So just further showing the inverse relationship of glass to weathering, I used Nesbitt and Young's analytical equation to find out the CIA, which is the chemical index of alteration, that shows as weathering increases, glass percentage decreases. So as the glass is decomposing, it's reacting with the water and changing its weathering, so into these highly weathered products, which is then leading once again to the retention of the iron, aluminum, and titanium, because that is sorbing to something, which we'll get to in a moment, and causing an increase in concentration. As glass goes away, the insoluble elements are staying, and the soluble elements are leaching out into the water and decreasing in concentration. All right, so what does this look like schematically? Just quickly showing, this is just a simplified structure of what a glass might look like. So we have our SiO2 tetrahedra that quenched with an arsenic ion in the middle of it, and as weathering occurs, the arsenic is released from the glass, and we're about to find out what happens next. So we have these arsenic ions floating around, looking for something to sorb to. Let's find out what happens. So the next hypothesis we used based off of lots of prior research was the tendency for arsenic sorption to iron hydroxides. And we had originally field data showing that there were iron-rich minerals in the volcaniclastic sediment of the region. So this is a mineral called goethite, in which is quite iron-rich and is an iron hydroxide polyatomic metal. And so using the understanding that Manning et al. Published in 1998, we're able to see that iron really easily sorbs to these iron hydroxides using something called bidendate by nuclear bridging. So essentially using X-ray absorption, Manning was able to establish that there's a really tight bond between the arsenic metal ion and the polyatomic metals of iron hydroxide to form these kind of compound structures of arsenic and iron hydroxide. So this was the working hypothesis. And there was more research by he et al. Showing this positive correlation of arsenic and iron. And in addition, Herrera-Murillo showed that there was this positive correlation in the geochemical data as well. So this is just more research correlating arsenic and iron through the sorption to iron hydroxides. So what happened next? This is the hypothesis, is that the arsenic is trapped in the glass, it's released as it gets in the water and chemically weathered, and then it sorbs to the iron hydroxide because of this tight bidendate nuclear bridging of a goethite mineral such as iron hydroxide to the arsenic in the supply. So I was able to find evidence for this hypothesis using the trace element data. So here we see that the correlation with iron oxide is different for soluble and insoluble elements. So iron here is controlling the mobility of the arsenic, the lanthanum, and the titanium. We see this positive correlation between the data sets. And on the contrary, we see an inverse relationship between the potassium and the strontium, which, as we said earlier, are those soluble elements that are just leaching out into the water supply, while these guys are sorbing on to the iron hydroxides and the goethites in the minerals. So just looking at this a little bit closer, we see the positive correlation between arsenic and iron oxides in the field. In addition, as I said, Herrera-Murillo didn't make any graphs for it, but did publish that there is a positive correlation between the water supply in Bagaces and Cañas of 0.51 R squared, meaning that as there was arsenic, there was also iron in a similar ratio. So not only did our volcaniclastic sediment data prove that there was a positive correlation between these two elements, but so did the geochemistry data of the water supply, further correlating that high arsenic concentration is equivalent with high iron concentration. So what does this all mean? In order to unearth what the real meaning of this is, I've been using EH-pH diagrams, and I'll quickly explain this. So EH on the y-axis here is the measurement of oxidation and reduction potential. So as EH goes up, we're gonna have more oxidizing occur. and pH is acidity. You may have heard of that before. And so what these plots show is the stability fields for these two elements to exist in the aquifer system. So what the red dot shows is the normal conditions. So this is under normal conditions, well oxidized, aerated aquifer in which the stability field is neutral and things are at equilibrium. We have our ferrihydrite, so we have our goethite mineral, and we have our arsenic ions sorbing to each other. Everything's great. So the question then was, what is shifting the stability field to get the arsenic to actually leach into the water in dangerous amounts? And we found that that was the introduction of organic material. So what happens with the introduction of organic material is, as you can see demonstrated by these black stars, is in an aquifer with anaerobic conditions. So as the oxidizing potential drops in these regional aquifer systems, then the iron and the arsenic become insoluble and are able to leach out into the water supply. So the introduction of organic material causes iron to shift from iron 3+, which is solid, so those goethite minerals, to iron 2+, which is aqueous and is therefore in the water supply. In addition, it has a similar or exact same stability field shift with the sorbed arsenate, which is the solid version of the arsenic, to the soluble arsenite, which is the aqueous, which is where we see the introduction of dangerous levels of arsenic into the water supply after they are released from the goethite minerals. So the transport of arsenic into groundwater, we saw this figure. Arsenic is trapped in the glass, it's released from the glass, sorbed to the iron hydroxide, and then finally, with the introduction of organic material, the dissolution of the arsenic ion and the iron ion are therefore put out into the water supply and leached out in dangerous levels. So this leads us to kind of the further overarching question of this research is, what is this organic material coming from? There's been lots of research around the world, as shown here in this figure, in which different sources have contributed to these oxidation changes in the stability field. So is it landfill, is it sewage, is it oil, is it agriculture? And what is shifting the stability field to cause these soluble arsenite ions to get into the water supply? So this is the overarching question of the thesis that has led me to further investigation and further curiosity, really. And so just kind of bringing it back all together now in our closing few moments, we're going to look at a hypothetical model which focuses on iron hydroxide. So here we see the Paleosol, in which arsenic originally occurring in the volcanic glass. It is then reciprocated or absorbed to those goethite minerals. It is then buried because these are immobile, right? They're not leached out into the water yet. Buried, 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 and then all of a sudden they're introduced to this condition, the change in condition shown by the different levels of kind of dashed lines here, because of an introduction of organic matter. So the organic matter shifts the stability field so that the arsenic and the iron are then oxidized using pretty much the bacteria, which are creating these oxidation reactions and preventing oxygen from mixing with the other elements, and therefore the release of arsenic and iron into the water supply, which is then getting extracted by the drinkers and the farmers of Bagaces and Cañas. So conclusions of my thesis is that the primary solid phase of arsenic is volcanic glass. Weathering of volcanic glass leads to arsenic fixating onto the iron hydroxides. Then the secondary solid phase of arsenic is iron hydroxide, so it's sticking to these goethite minerals. Then the reduction of iron hydroxides in the presence of organic matter causes the release of arsenic into the water solution. And lastly, there needs to be future work done in assessing the potential source of organic matter. What is contributing? Is it landfill? Is it sewage? Is it just local trash pickup that is getting into the water supply and causing the release of these dangerous levels of arsenic? So once again, I'll come back to this slide and just say, I obviously can't provide all the answers for the people of Bagaces and Cañas, but I am one of the first people to do research into the source in these specific regions, and I'm excited to at least launch them in a direction of further investigating this source of organic matter, which is causing the leaching of dangerous levels of arsenic for the civilians of Bagaces and Cañas. I'd like to take a moment to thank the incredible people that have helped me over this last year. Of course, Dr. Pete Ryan, who has been there through it all and also has been to every one of my home basketball games, along with Dr. Christina Wurlowski as my second reader and figure master, as she has helped me produce lots of my plots and actually just the reason I'm a geology major to begin with. Jody Smith, who was really helpful with all of the instruments and helping me hack on to the computers at school from home these last few months. Eileen Brunetto for helping organize everything. Dan Ellison, who was my lab partner as I was in a boot and on crutches, who helped me get a lot of the lab work done. Maggie Ryan, who was my field partner, helping along the whole way and supporting us at the Aguas lab, specifically Alex Cobb. And I also just want to give a huge congratulations to all the other geology seniors who are now done with their theses and have defended them, and glad to be the last one and just cheering you all on. And of course, my basketball team. So thank you all so much. And I'm excited to take some questions.
Yeah,
Thank you. Let's see.
So unless it gets too awkward, I think we could, if somebody has a question, just unmute and say it. And if Kira or I need to referee, we will. But maybe there's few enough participants that we can do it somewhat organically.
Oh, wait, I need to figure out how to get out of, oh, here we go. Okay. Oops. Do you all still see my screen? I can't tell.
Yeah.
Okay, I should do it. Any questions? Okay, if not.
Yeah, Kira. Oh, sorry. Go.
Is this like a unique combination, that there's the combination of like the organic material causing the arsenic and the iron to leak out, or is it seen with a lot of volcanoes and wherever the volcanic like ash is?
Great question. So yeah, it is not a unique combination. This is a something that surprised us actually about halfway through the thesis when we saw this really big correlation between the arsenic and the iron, which then led us to understanding and doing a little more research that this is really common around the world. Actually, part of the research I did last summer was looking at an oil spill, which was allowing for these reducing conditions that allowed for arsenic to get into the water supply there. So there are other research throughout the world showing what these organic matter infiltration could be. But I think what's interesting here is that we don't really know at all. So it could be the sewage, like I said, could be the local landfill. And further research, maybe Pete's next student will do kind of a geographical mapping of potential sources of organic matter. But it is well studied and well established that that's the case. Great question, Sabs. Thanks for being here.
I had a question about the organic matter and how you might know that, like, is it high in abundance, or why it's not just typical ground mass organic matter?
Good question. Well, to be honest, you'll probably know more about it than I am as a biology person. But what I do know is that the shift in stability field that we do see, it can only be attributed to that amount of organic matter. So the other hypothesis was just that the pH of the water was, actually, I think I might have, let's see if I should share my screen again. So using Herrera Murillo's, groundwater data, he also published the pH of all the local water here. And these pH levels are not significant enough to just shift the stability field of and create these reducing conditions. So that's why we're led to believe there has to be another source that's causing the shift in stability fields, because the natural aquifer is not of high enough pH to do that itself. But I wrote extensively about that in my thesis, kind of saying this is one option, but this isn't the case. Rather, we have to look more into the organic matter. Thanks.
Thank you.
Kira, what are the activists on the ground like as far as making policy changes, behavior changes? It looks like there's been headlines. There's groups that are trying to help each other fix this problem locally. What's it like in terms of matching the data with what's going on the ground?
Great
in the
question.
community?
Thanks. So what we're seeing is there were filtration systems put in place after the data, was established. So the local government and environmental communities do have the water being filtered. So the levels of contaminant is not as bad right now, but there is lack of kind of academic research that's linking with the activist and government community, showing what the source of the arsenic could be. So kind of working backwards in time. Costa Rica itself is like actually really great in terms of sustainability and environmental movement. I think they're like on track to be carbon neutral by a year much sooner than anyone else. So they have a lot of good energy and resources contributing to environmental planning and stuff like that. But there has just, this is pretty recent. I mean, it's only within the last 10 years. So I'm hoping that potentially with the data that Pete and I will publish, there will be more collaboration with the activists and government communities and scientists to actually kind of work backwards to the source of arsenic. But the People's Voice of Guanacaste, which organized that rally in 2013, from the articles I've read, have been really great in helping supply more information and demand answers for the people. Thanks, Nadine. Thanks for being here.
Kira,
Hi, Dad.
is there any epidemiology that you've seen or are familiar with about incidents of disease or other effects of arsenic in the community?
Yeah, so there was a study that was linking the kidney failure to, I think it was linking like morbidity index to kidney failure to arsenic levels in the groundwater. And they actually found that there was no direct link to levels of arsenic and kidney failure. So the questions of exact kind of future causes of arsenic contamination are still a little bit unknown. But if you're curious more about the health factors, here's my little schematic of it, just showing that the long-term effects they're not that well established in terms of what is actually happening in this area, like I said, because it's only been 10 years since they know that arsenic has been the problem. But one study was, like I said, trying to match the kidney failure to morbidity to arsenic, and it was actually shown that there was not a big correlation between that. So they're going to continue to look into it. Thanks, Dad.
Kira, that was fantastic. Thank you.
Thanks, Jen.
I'm wondering if you're familiar of a similar situation anywhere else in the world now, or historically.
Yeah. Great question. So arsenic contamination is definitely an issue globally. A bunch of the studies that I used for a lot of my research take place in Argentina in the Chaco-Pompeian plain, in which pretty much the exact same thing is happening. And so that is a region in which we will be able to kind of compare the data even further and understand we can look at what their contributing organic matter factors are and potentially compare that to those that will be mapped in Bagaces and Cañas region. There's also a lot of arsenic contamination in Indonesia due to similar subduction and other related issues. So it is a global issue, definitely. And well, I guess something important to say is arsenic is everywhere. So arsenic is in all rocks, in water, and whatever. It's just, you don't really pay attention to it until the levels are dangerous enough. And so we probably have arsenic, I don't know, in all of us in some capacity, but in low enough levels where we're not feeling the health effects and where it's not being mobilized in the aquifer because of organic matter to reach these really dangerous levels of contamination. Thanks, Jan. Thanks for being here. I hope your arm's okay.
Hi, Kira. It's Barbara.
Hi, Barbara. Welcome.
Hi. Super nice talk. You know that arsenic can also be mobilized by oxidation of pyrite, where arsenic is present with the iron sulfide. Did you examine that mechanism of mobilization at all?
We did not, in the scope of this thesis. We didn't have the time or resources to get it all done, especially in the last final crunch of the lab time. But we didn't see major indicators of high levels of pyrite. Instead, we chose iron and glass as the hypothesis we are working for. But that is definitely worth going back and doing further research on uncovering.
Thanks.
Thank you. Thanks, Barbara. All right.
Kira, this is Peter. Hi, good job. Really interesting talk. I'm curious from your anecdotal evidence of being in Costa Rica, where you think the organics are coming from, and also what alternative drinking supplies are there, if any, for the local communities?
Great question. So first off, Pete just, we actually kind of came to this conclusion within the last week or so. So we haven't done much speculating, but Pete has told me about some local, I think, landfills that could potentially be the source of this organic matter. So they know of some places that could be improperly disposing of landfill and other waste products nearby, and just further research into these specific areas should be done to understand. And then your second question was other potential water supplies. And there is, I think I read once about a potential aqueduct coming from some different regions of Costa Rica, but the thing is that a lot of the water you see in Costa Rica, especially near the volcanoes, is geothermal. And so you don't really want to be drinking geothermal water for a lot of reasons. But yeah, like I said at the beginning, 88% of Costa Ricans drink groundwater from the local and regional wells. So I think as much as they can mitigate this issue and continue to have people drinking the groundwater, it's remained a fruitful source and clean source up until recently, obviously. So I think the main kind of mitigation tactic will be to fix this rather than try and build a new system.
I have a question about also on the topic of the organic matter, and I think mostly just a clarifying question. So when you were talking about the presence or elevation of organic matter, are you talking about it being in the water? So like it would have been leaching from a landfill then into the water, and that's causing also like these iron oxide minerals that are already in the water to then, like, is that process happening in the soil or is it happening in the water? And if it like happens in the water, like what does it look like? Like, are these particles large? Is this like really microscopic? Yeah, I was just kind of interested about that relationship and like where it's happening. And like, often with organic matter, I think more about in soil than in the water. So
yeah, you're right. That's awesome. Thanks, Alex. So as you can see in this hypothetical model, the organic matter is absorbing on sand. So it's actually in the solid phase. So the goethite minerals, which is those iron hydroxides, and the solid arsenate are sorbed together as a solid compound. So as a rock, or as you could see earlier, as those iron-rich samples. And once the organic matter, so whether that is landfill or sewage, gets into the aquifer sediments, it then invites reducing bacteria who create this environment where oxidation is prevented. So, and then once the organic matter is absorbed on or creates this reducing environment, then the minerals themselves break down and release the elemental form or the soluble arsenite into the water. So the breaking down happens in the solid phase, not in the water. Did that answer your question?
I think so.
Cool.
I can call you later and ask you more.
Okay, sure. I don't want to take up too much time of anyone's. So any final questions?
Sure, great talk. I've got a question.
Oh yeah, hey Albie.
Hey, so is there anything that you discovered along the way that didn't really fit within the context of this presentation or your thesis that may be an area for future research?
Great question. Well, the entire iron hydroxide thing I discovered along the way. Pete and I went into this thinking, okay, just the volcanic glass is leaching out arsenic and it's getting into the water. So we kind of went with that preliminary method, and then the data actually showed that something more complex is happening. And we only uncovered this actually since I've been home, so we've never talked about it in person. But that was really surprising because we were able to actually not only understand, so my thesis just started out, what's the source? So the answer would have been glass, but then it evolved to not only what's the source, but also how is it moving and how is it getting into the water, which I found to be a really, really interesting surprise and discovery, because not only could we now think about mitigation tactics that maybe address the glass, but we can also think about them that address the iron oxides and how they're being mobilized and transported throughout the aquifer. So kind of a more holistic understanding, as you can see on this hypothetical model, how we get from up here where the arsenic is to here. So that was my first jump of my thesis. My attempt was just to be there to there, which in turn led to a whole much greater analysis throughout the aquifer system. So I think just overall that whole discovery was really awesome. Thanks, Albie. Thanks, Anna. Awesome.
Okay, going once, going
Uh-oh,
twice.
Chris Paiza looks like he's ready to talk.
Okay.
Never mind. Cool.
All right, so if there are no other questions, speak now or hold your peace. We will ask that everybody who's not Kira or a geology prof leave and wish Kira well on her defense.
Thank you all for being
go,
here.
Kira.
Really appreciate it. And good job to all the other seniors. Woo! Here, graduation hat.
Defense.
Nice, good one.